This meeting is being recorded.
Okay, so today is the 20th of October 2022, and today's Tech Hour is same inputs from the XML Catalog. I'll just repeat a few things from the webpage for this talk, which is that getting the same inputs from the same outputs is really important, particularly if you're something like a publisher who wants the documents to be archival, because STEM literature, for example, can have a very long life, and journals have a back catalogue, which is important. And it's, well, perhaps we could say this, that publishers have been caught by the move to electronic media, and they don't want to get caught again by changes in formats for electronic media. So previously, their archival format might have been, well, actually, one publisher I worked at, it was photographic prints, photographic negatives from which litho prints were made, from which litho plates were made. That was their archive. And prior to that, actually, the archive was funny things called flongs, which were paper mache things from which rotary images could be made for printing. So the archiving was all quite interesting in publishing before the electronic media. So they do have an interest in archiving. But anyway, Don Knuth was in that tradition, and he was writing a book that was dealing with truths that are closer to eternal than most of the ones we deal with. And he wanted his work to persist, and he wanted tech to produce the same outputs 100 years from now as it did from today. Now, when it says the same outputs, from the same inputs. And my focus is not on the program that does the transformation, but on making sure we get the same inputs. Einstein is supposed to have said madness is repeating the same calculation and expecting a different result. Well, in some situations, madness is repeating the same calculation and expecting the same result because it so rarely happens or because it's so difficult. So this is all about getting the same result. And to deal with the bloat, the Git bomb that Tech Live sort of provides, where you have an installation that is perhaps a gigabyte and you change one line in one file, and you have to have a separate installation to deal with that one change in one file, or maybe you don't, but things are sort of fraught and difficult sometimes. And so many people say, oh, show us your log file and show us this and show us that when you make a report of fault. And it's never a question of, here's my calculation. Do you get the same result? Can you explain why I'm getting the result I'm getting? You don't say to somebody, well, I've multiplied 5 by 7. Sorry, I multiplied 7 by 8 and I got 54. Can somebody tell me why that's wrong? And they don't say, oh, show us your calculation. They can do the calculation themselves. Sorry, I didn't do that example very well. But ideally, when you're reporting a bug, you should be saying, here's a calculation. Here's the typesetting of a document. I think it's wrong. Can somebody explain to me what's happening? And the person should be able to reproduce the calculation. This is one of the key things about science, is reproducible results. And so reproducible calculations is very important. And having reproducible inputs is very, very important. I believe in biology, they have standard cell lines that are used for experiments. So they produce these standards. And the National Institute for Standards has standard cigarettes for testing the flammability of sofas. They're quite expensive. And all sorts of other things like that. And going way, way, way back, I'll put my arm out for a reason, which is standard weights and measures and lengths, the qubit, and all those things were the responsibility of the authorities, which was the king. So I'm going to start some screen sharing, and I've got something like 6 or 7 examples to show you, and that will take us on a journey. Are there any questions before we start on that journey? Okay, we're okay. So I'm going to start sharing the screen. And it's the entire screen. And here we go. Okay, so on the left of the screen, you'll see a file called tutorial1.py. And can you see that file? Excellent. Is it big enough to read? Yeah. Okay, so what I'm going to do is I'm going to run that file in Python, and the -i that I've just put down means leave me with a Python prompt rather than just end. So, oh, sorry, what's that? Python 3. Okay, so that's now given me a hint, which you can see in the source file. There's no magic about that hint. And it tells me to type book equals parse book.xml. So book.xml is a file in the same folder. And we're going to load it and parse it. And then we print strf from element book, so that you can see what we've got. And now, is that window big enough, the console window? I think it is. Yeah. Now what we've got is what's called an XML include document. So the book is the book, and it has some elements in it that include the front, the body, and the back. So this is like the include in LaTeX. You can include one document in another. And this is the same sort of thing. It's got different features, it works in different ways, but the basic picture is the same. That you're going to construct a new document, or what is effectively a new document, that is obtained by pasting in, replacing the includes by the thing that should be included. So instead of here be dragons, you have dragons. And there's a command that we can apply to these elements that my software provides called xinclude. So I've just run that command, and now I'll have a look at the book, and you can see the book has now got a section called front, a section called body, and a section called back. So we've got 4 pieces of XML: the book, the front, the body, and the back. And we've loaded the one, and then we've expanded or dereferenced the includes, and we've picked up the rest. This slide is this unit is important because it allows me to state what the problem is. So I'm going to exit that, and I'm just going to show you what book.xml is. Well, you might think, of course it's that. But don't miss the important point. Book.xml is a file. It's a file on a particular machine at a particular location. And if I do cat front.xml, well, we get what we expect, and so forth for the others. So the object is to repeat this same calculation: book, front, body, back, but in a reproducible way. And that means that the files we use, the 4 files that we use, have to be specified in a reproducible way. Now, one way to do it is to say, oh, you get it from that location. Here's the URL for getting that file. And that's fine as long as the URL continues to exist, and whatever is stored at the end of that continues to remain the same. But it's no guarantee that that will happen. It may be that there's a glitch in the transmission, and you sent the right file, but it was received wrongly. All manner of things can go wrong. But the most likely thing that goes wrong is that one of these files is changed and you don't know it. And that's why people, when they do bug checking, say, well, let me see your log file at least, because I want to know what's going on. I want somehow to dig in and find out why your machine is different from mine, and I'm worried about inputs and whatever. So that's enough for that. You can ask questions if you want to, and I can see you. So put your hands up if you want to ask a question. And the next thing that's going to come up is, believe it or not, tutorial 2. Oh, this is quite a big one. This is quite a big one because I use a resolver. Now, what's a resolver? In this case, it's a resolver where it resolves references. So when it says book.xml, it actually provides something that functions as the book. So what we're going to do here is we're going to follow the script, and then we're going to see how we did it. So it's a slightly different process here. We're going to have a look at what happens, and then we'll see how we made it happen. Now here we have to supply the parser by which we do the parsing. I don't think we did last time. We certainly didn't need to. So, and we didn't do it last time because we didn't see that before, did we? So that's a message from our special resolver. We have my lookup, which does the resolving, and for some reason it's skipping. So now we've got the book. Let's print the book. It's exactly the same as before. Now, let's expand the includes. And my lookup is getting its nose into the process again. It's like a busybody that doesn't let anything happen unless it says so. So it can, like Maxwell's demon that sort of opens and closes the door so that all the busy molecules go on one side and the other ones stay on this one. So this is a sort of busybody that intercepts things and, if you like, does a man-in-the-middle attack. That's one way to look at it. It's a sort of man-in-the-middle attack, but like Maxwell's demon, it's a benign man-in-the-middle attack. Let's look at what we've got. How have we changed the book? And we see it's changed in a completely different way. So what we've learned here is that by putting in a resolver, we can avoid the lookup from files, and we can substitute in whatever we want. I'll say that again because it's really important. A resolver means that we can use a file name, but we don't have to treat it as a file name. We can just do whatever we want with that name that we're given and feed something back to the XML document to resolve the include. So now we can look at the lookup thing. So I use a resolver that comes from the software that I'm using as a base class. So I'm adding some functionality to the standard resolver. And what I'm doing, in fact, is I'm changing the resolve method. And to begin with, I say print so that we know it's working. And if the URL is book.xml, we'll skip this resolver by returning none. And then matters will go on to the next one, which is why we got something coming in. But otherwise, we'll resolve the URL. And what we'll do is we'll give a value. And here it is. It's the string that we see in the console. And then you return that as a resolved string. So what happens is, just look at the resolve method. A file name comes in and we say, oh, well, I'm not going to go to the disk. I'm lazy. I'll just send that file name back again with a bit of padding around it. And the next lines create a parser, a new parser that's standard parser, but we add to it a special lookup. I'm going to give you a really good opportunity to ask a question here, because this is really very important. And it took me a long time to understand it because I didn't have examples in front of me. So I hope you can do a better job than I did. We okay, or do you want to ask a question? Okay, we'll move on. I can always go back. So here's the third example. Let's put the screen up. Now this is almost the same as before, but it's got something really very, very, very important happening. The only difference is that, I don't know if you can see it here. We've got the value and we wrap the value inside a fake file object. And a fake file object is a very, very weak imitation of a file. We'll see what it is in a moment. All it's got is a read method. And then we return the fake file. And instead of doing a resolve string as the return value, we do a resolve file as a return value, so that the system knows that it should treat what it gets as a file and not as a string. And I'll run the software, and we should get exactly the same as before. We've got a different MyLookup, but we've done the same transformation to the book. And if I open the tools file for you, you can see that the fake file stores the data it's got, and the return method simply reads a character from it. I think there'll be a demonstration later that shows this. The key point here is that when we read a file from disk, we get a stream. We say, give me 255 bytes because that's the size of my buffer. And it says, here are 3 bytes. I hope that's enough to be getting on with. And then you ask for some more, and it gives you some more. Sometimes you say, give me 1 byte, because I know that if I ask for 2 bytes, it will block. All sorts of things can happen, but you ask for how many bytes you want, and you get how many you get. And when the stream is at an end, and you ask to read from it, you get back nothing. You get an empty string. So the key thing about this is it shows us that the XML parsing system that we use doesn't need a file name. It doesn't need a file. It just needs a fake file, by which I mean something that has a read method. And when you read, you get at least 1 byte back, unless the fake file is empty. So that's going to be important when we come to interact with the Git repository. So let's see what we've got here. We'll do what it says. Okay, so now we've got a dictionary, a Python dictionary, and each file name has been mapped to a Git object identifier, which is this awfully long string. And let's have a look at the tutorial. Now, I'll tell you later how I got this information. I'll tell you now, actually. I committed the files that I had to a Git repository. Then I told Git to tell me, what's the tree you've got? And this is the information it gave me. And I've just rearranged it the other way around. So instead of giving the object identifier first, followed by the name, I'm giving the name first, followed by the object identifier, and using it as a dictionary. So what that means is that I've now frozen everything. The book.xml has to be the object whose Git object identifier starts 127341. That's how we guarantee reproducibility, is that the resolver does not produce a stream, or rather it doesn't produce a stream directly. The resolver looks up in a catalog, and then from the catalog gets the object identifier, and from the object identifier we get the object. So let's look at 5. What's this one? Okay. So perhaps a little, what I've done is, in my mind, I said, what's the process that we have to go through step by step by step to secure our goal of our XML parser picking up the data from a Git repository? And I've broken it down into about 6 or 7 steps. And here I'm just doing the steps one at a time. And at the end, we'll have a grand finale where we'll see everything. So this is a complicated bit of code in the sense that it's sort of a bit shell scripting and uses sub-processes. So let's follow the instructions, over here. So here's a Git object identifier, which are very useful for computers because they know that allows them to say we've got the right object. So here's the Git object identifier. And we're going to create a fake file. Actually, it's a bit more than a fake file, but we only need that it's a fake file. But we also need to say where we get the thing from, because there's no universal Git object store that has all possible objects in it. And it's going to be in a file, or directory called my book. That's the only need we have of a file system. And we get from it, if we can, the object with the object identifier. And what I should have written is cat blob. So there's fake file. And now we'll read 5 characters from it. And let's read another 3. And we can read 10 more or 19 more. So if the section is quite long, if it's a megabyte or even 2 megabytes, we don't have to read 2 megabytes into memory. We can just read whatever's convenient. And the parser will ask for what it wants, and the system will give whatever it thinks it can. So that's pretty much the standard I/O, except it's been a bit mediated. Tutorial 6. I've no idea what we got here. Sorry. Oh, what's happening here is I've got the value here, but I'm not actually using the value. So I should have deleted that. What I'm using is I'm using the fake file as part of the resolution. And the resolution is giving me a resolve file. So the resolver is the same as before, except I get a Git object ID from the catalog. And the catalog has everything I need because that's the way I built the catalog. I built the catalog to have the right stuff in it. So let's have a look at, this is tutorial 6. So book equals parse. Oh, sorry. And we need our custom parser because the parser's got a custom resolver. So there we use the custom resolver to resolve the book. We hadn't done that before. Previously, the book came from the disk. But this time, the book has actually come via the custom resolver. Look, we see it's happening because we got the lookup message and we returned a resolve file with our fake file. And our fake file was a cat blob from the Git repository that is my book. So let's now see, there's the same output. That's the same output from the reading of the file that we had at the very beginning. Exactly the same output as we had from the very beginning. If it wasn't exactly the same output, there'd be something wrong with the whole system because the input was exactly the same, even though we get hold of it in a different way. So now we can do a bookx include. And again, my resolver is going in and the stuff is coming from the Git repository. And we've got from that exactly the same output because we had exactly the same input as my first example. But none of the inputs came from disk. They all came from a Git repository via a catalog, via an object ID. And so if you run the same calculation against another Git repository, it will either give the same output or it will fail because it can't find one or more of the objects. And if that doesn't happen, it's a bug in the system. It's a bug in Git or it's a bug in libxml or something else like that. But the expected behavior is that when you put these inputs in, you will get exactly the same outputs. Now, the expansion of the XML includes is a fairly trivial calculation, but it does rely on consistency of input to give consistency of output. And here we've managed to get consistency of input by using a Git repository, which is the way in which software developers ensure that they have consistency of input by using a Git repository. I don't know if we've got tutorial 7. Let's see. No, we don't. So we're finished now. Before I stop screen sharing, let's go back to tutorial 1. Nothing has happened. In some sense, nothing has happened. Except we've changed we're using a different parser to parse with. this is using the default parser, and we're using a slightly different parser. So that's exactly the same as we had before. And that's exactly the same as we had before. And the only difference between the two is that we got the inputs not from disk, but from a Git repository via object identifiers, and that gives us the consistency that we're looking for and we're seeking. The other difference is that we got the diagnostic messages that tell us that the resolver was going through code that we had written that redirected the file requests. So if you know tech, there's a piece of software called, I think, kpathc that is, so to speak, redirects the file requests, but it does it a different way. The tech tool says, you give me a file name and I'll give you a different file name. And then you go and open it. Here, you give me a file name, I'll give you an object identifier that uniquely identifies the file that you should be getting. And then you get it from the Git repository. And if the Git repository doesn't have it, then you get an error. Or if the Git repository pretends to have it but returns something else, you can check that it's correct. And the Git repository can hold 50 different versions of the same file, all slightly different versions of your inputs, different versions of your document, and the usual version control stuff. And your catalog, by changing one line in the catalog, you can get whichever of those versions you want. So you don't have to store billions of lines of code, billions of lines of almost identical material, in order to move from one version of TechLive last week to this week. All you need is the changes between the two versions and a list of which file belongs to which version. And then the change from TechLive last week to TechLive this week is some additional files in the Git repository and a different catalog whose entries change only for the files that have changed. So if you remember the catalog, it was a dictionary with keys, book.xml, and so forth. A version moving to a different version is simply keeping the dictionary the same, except you change some of the Git object identifiers as keys. And if you have new files, you have additional entries in there. If you have fewer files, you have fewer entries. So that's what's going on. And from some point of view, what we've got here is got the usual business of Git version control, except we're not using any commits at all. We're just doing it at the level of lookup tables for object identifiers and so forth. I think that's enough for now. I'll stop sharing unless somebody stops me. We can have a discussion. Right.
I understand the basic principles here, but I think for ordinary users, the exposing of object identifiers as a long, unintelligible string is probably a significant barrier to this approach. And I'm not sure how one could hide the object identifiers in such a way that users wouldn't accidentally get them wrong. I mean, inside a text editor, it's very easy to change a character, insert or delete a character, and so on. And when you corrupt an object identifier, you can't tell by looking at it that it's been corrupted.
Okay, so the object identifiers, there's two things you need to distribute, I think. The one is the files that you're going to input. They have to be distributed. They can be distributed as pack files. And if the pack file is wrong, we'll find out. if the pack file is missing something, we'll find out. You won't get, if there's an error somewhere, you'll be told about it. And the other thing you have to do is to distribute the catalogs. Essentially, I'm calling them catalogs, and for XML they're called catalogs, and I think it's a good way to look at them. Now, Git is built on plumbing, that's the word they use, very similar to what I've described for you. So internally, Git works with object identifiers, and I can show you that by screen sharing, which I might do in a moment. Git works internally with object identifiers, but then gives you useful handles, which are branches and revisions on branches that allow you to point to whatever it is you want to. So that you very rarely, you don't need to point that often to these really long identifiers. And so in practice, everything can be hidden from the user, actually to a greater degree than it is with Git, because Git, you have all these revisions that don't have names, whereas with TechLive, if you're dealing with TechLive in this way, it will be TechLive 2002 week 36, week 37, week 38. Each of those will have a catalog, and you have to specify the catalog, and you have to put the catalog under version control. And if you want to say, I want to be sure that you've got the same stuff as I have, show me your catalog. No, give me the secure hash of your catalog. Better still, have your software send me the secure hash of your catalog. And by doing that, I can check that the identifiers are the same. So to check that everything is tickety-boo, all you need is one of these long identifiers. And that's the same with Git, and it's the same same system that's used when you say, here's the ISO image, here's the checksum for it. You should check the checksum before you use and trust the ISO image. So in that respect, it's no worse than before, but it has the benefit that it becomes quite easy to ensure that you get identical inputs. And archiving becomes a lot easier because all you have to do is store one copy of every different file. Every file that's different, you just need one copy of it. You don't need to store hundreds of copies of the same file in different places. And the other thing you have to store, of course, is the catalogs. But the catalogs are relatively small because it's the name of the file. And it doesn't actually have to be the file system path name of the file. It can just be cmr10.tfn if that's what you want. It's the name that the human being uses. And then you need the secure hash, which isn't as big as it seems because it's base 16. So it's about 32 bytes or something, 40 bytes or something. So and if you're fussy about size, you don't have to secure the whole of the catalog. You just the differences between the other between the previous catalog and the next catalog. And all of this is exactly what Git does, and Git is tremendously efficient. Now, there's one more thing I want to say, which is this is a technological proof of concept rather than a user interface proof of concept. And I've done it in XML because XML has resolvers that allow us to pass file-like objects rather than file names, which is what the text system does. And so it's much, much easier to implement because I don't have to create files. I just have to create something with the read interface. Now, one of the tasks that is now possible, given what we've shown to be possible, given what's been shown here, is to develop an interface whereby the burden that you rightly identify, Nelson, becomes manageable. So what you've done is you've said there is this burden and it has to be made manageable. Or at least that's my interpretation of it, is how do we make that burden manageable, which is a sort of usability problem. And we can at least do as well as Git does.
So in the context, say, of collaborating authors, they start out with, say, the book that they're jointly writing, and they have a catalog. And now the first author updates chapter 1, and the second author updates chapter 2, and so on. What is a good way to ensure that all of the authors on a given day actually have all of those? Is the idea that they would most likely share a common repository so that all of the catalog object identifiers will be the same for all of them?
The best way, I would say, certainly at present, is to use Git, even though it sort of has its problems as a version control system. And that's one of the great benefits of using Overleaf, is it integrates well with, I'm told, with the Git repositories such as GitHub and GitLab. I think I'll do a share because it'll make things a lot clearer. So, share screen. A screen. So here's my Git repository. Now, this is jolly interesting. Git log, initial commit of stub book. It has this information here in brown, which most people ignore. That's the object identifier for the commit. We're going to have a look at what Git says that commit is. It's got a tree. Let's have a look at that tree. There it is. Why are we not seeing everything? There's that tree. And this is where I got my catalog from. Now, I haven't checked it, but I think we can do this. No, it won't work. We can do something like this, and it will actually work like a file system and give you the object. So I can't prove it to you now, but it is the case that once you've got the object identifier of a tree, you could then refer to everything in the tree through a path using ordinary names. So there's only one thing that needs an object identifier, which is the root of the tree. Then everything else is done by paths.
What if you use the commit hash for the back file, the back.html
Sorry?
file? What if you use the hash, the 3E1BA2, instead of adding the /back.html to the last? Would that work?
Well, if I,
because the hash should identify those files uniquely, right?
okay, so yeah, what happens if we do that? Okay, so if we do this, oh, sorry. I'm sorry for this delay. Oh, I'm pressing the wrong key, that's why. That types the file. And possibly, yeah, this is actually what cat blob does. You see here we've got cat file -p, which means print it. So if I do cat file, this guy, if I got it right, that's why we've got the value we did over in tutorial 5. So all I'm doing really is I'm using low-level Git commands, but instead of building Git on top of them, I'm building something that is more to my flavor, more to my taste. And my particular taste here has been driven by the desire to make the XML include command fully archival. That was my goal, make the XML include command fully archival. And by archival, I mean every data access goes via a Git repository and object identifiers obtained via a catalog. Now, the resolver, you can have multiple resolvers, and you can say, if the file name begins with local slash, then don't look it up in the Git repository. That sort of stuff can be done. So you can have a resolver for this sort of name and a resolver for that sort of name. And even if your rules on names are higgledy-piggledy, you can have a resolver that just says, for these particular files that I happen to be interested in, have a look at them in my directory here and get everything else from TechLive. So you don't have to move your files to any particular special place so that the KPathC stuff picks them up for your job, and you do it in a way that's completely logged. So one of the key things about this is that you use local files, then you must have a convenient way of moving from local files to global files. Not global files, but archival files. So I'm going to stop the share, if that's okay. I think we've had good questions. I'm pleased with the questions. I'm going to stop the share.
So I can see if we were to take TechLive and replace the KPath search library with another one that, instead of looking at the file system, look at a master Git repository, then a user could run Tech with a pretty small installation on the local machine, because the only files that ever need to be pulled over would in fact be those that are actually used by that document. This is the exercise we went through about a year ago in figuring out what was actually loaded for a modest-sized LaTeX run.
I think in my conversation with David, something really important came out, which is that KPathC does a similar sort of resolution, but it says, here, you gave me a file name. I'm going to give you back a different file name. And so that immediately says, and therefore it has to be found on disk somewhere, unless you're doing something really clever like user space file systems or something, which are quite complicated. Whereas XML, which was developed much later and with sort of different constraints, said, okay, well, actually, all we need is a stream that we can read, which is the whole point about HTTP. HTTP doesn't give you a file. All it gives you is a stream that you can read. And the resolvers I've written, you give it a file name, and you get back a stream that you can read. So what's happening with KPathC is you get back a file name, and then you open the file name that you're given. Here, you start with something that pretends to be a file name, and you use the stream that you're given. You don't open the file. We don't trust Tech to open files. all file opening will be done by the resolver. And the resolver will open the file to give you a stream that comes from the Git repository.
So each article would need to have this catalog associated with it, right?
Yeah. Yeah, think of it as a bit like, to typeset the document, you need certain fonts. So those fonts are going to have to appear in the catalog somewhere.
Right.
And you're going to need certain other style files.
Right.
But the thing is that well, here's a different way of looking at it, which is what I call portable tech documents, which is a bit like portable PDF documents, which is, with a portable tech document, it should come with a catalog that tells you what it needs. And there should also be repositories where you can go and say, here's my order, give me the stuff in this catalog that I don't already have. And Git already provides that. When you do a pull request with Git, effectively what you're saying is, here's a catalog of stuff. Give me all the stuff that I don't already have. And it might say, I don't have it. But if you ask for pull a commit, if the object identifier is a commit that's in the repository that you're pulling from, it will have everything. So the only reason why you need to enlarge the catalog is if not other resources are required or different resources are required. But if you've got a document already typeset and you want to reproduce the typesetting of that document, the only resources you need to get are the ones that are listed in the catalog. That's the idea.
I mean, this is very similar. I mean, in software development, like within Python, you have your requirements.txt file that tells you which packages you need, or your pip file that you would pass along as a developer, and they would load their environment with the correct packages, and you would get the same result. So I'm trying to place this all in the context of archive, and we often have people who are developing submissions, and what they see on their system is different than what we see on our system. And basically, I suspect if you polled 1,000, tech authors, they might each have a different version of Tech Live on their system, which means they may have a different set of files. So it's difficult to pass these around, and we have the same problem when someone downloads the source from archive and they can't build the submission. And so I'm kind of thinking about how this could come into play. I think someone would need to build this repository, like the master repository for tech, that would have basically every version of every package going back. And then each submission could just carry along a little catalog with it.
Yeah. Okay, so I have sort of built I've built a big Tech Live repository. I used CD images, and I can't remember how big, but sort of for 10 years of CD images, and you're not recording the documentation. It's sort of a few gigabytes. When I say a few gigabytes, it might be 5 or 10 gigabytes, right? But each year is itself, 3 or 4 gigabytes. So immediately you get some sort of large compression. But it becomes practical to say, for this document, you need this material. One of the things I've been very keen on is not checking out a whole Git repository just to run one document. Why don't you just directly from the pack file, pipe out the things that you do need.
Yeah. So for tech, would you need to recreate that file system somehow, like a very trimmed down file system, so that your standard LaTeX would be able to find those documents?
Well, LaTeX, at present, LaTeX finds things through the kpath-c, right? Which maps one file name to another file name. Now, if you've got a good handle on everything, and you've got a particular version of some particular version, let's start with the point of view of a reproducible calculation. For a calculation to be reproducible, you must have a secure hash for every one of the inputs. And you must also have a copy of every one of the inputs. Now, having a copy of every one of the inputs isn't too difficult. It might sound crazy and impossible, but it's not. You simply say, take all the inputs and you put them into a Git repository. And if you ask the same input, exactly the same input, to be stored 20 times, it's still only stored once. So you just say, store them all. And you say, oh, well, I stored 100 gigabytes of files, but it only added 1 gigabyte to the storage, or whatever. But you have to know for each resource that you use what its hash is. So the resolver could actually compute the hashes of the thing it pulls in. It could do that as a side effect. Everything that comes in, it can compute the hash of it, and it can also commit it to a Git repository if that's what you wanted. So that's one of the technical things, which is I've done this calculation using my messy file systems. I want an easy way of making it a reproducible calculation. And then I'll get a secure hash, a Git object identifier that tells me what that calculation is. And as Nelson says, I want an easy way to refer to that object identifier. And that's a tag, which is something that Git is very good at.
The relatively small size of, say, TechLive in this form, plus the fact that computer memories continue to increase and to fall in cost, suggests that for many people, all of TechLive could be memory mapped at the start of a tech run when they came to the office in the morning and remain memory mapped the entire day. And no matter how many times they typeset, they would never go to disk again. They would simply pull out of memory. And that could make typesetting fast.
Yeah, or another thing you could do is whatever's behind the system that gives you a fake file can just cache the stuff that's recently been, so you run the same document 20 times in a minute, and the stream that you have to read comes immediately from memory, and the memory might, there's no going to disk. But all that is sort of optimization. And if you like, my sort of concern is to get a line from A to B that is useful enough for other people to build on it. So to take a sort of, maybe a fake American example, from West Coast to East Coast, the first such line was the Pony Express.
Which went through my state.
Yeah. And in time, they built the railroad. And the railroad allowed the telegraph to carry through. But that first line was the Pony Express, or if you prefer, it was Lewis and Clark. They sort of... Actually, the Mason-Dixon line is a line on a map, isn't it, by Mason and Dixon, or whatever. It was just a surveying line. So what I'm concerned in this thing is to say, look, here's a way of gluing together two pieces of technology, inclusion of files, reproducing and calculations on the one side, and Git repositories on the other. And I've done it in the concept of XML because it's easier for me to do it that way. That's one thing. Secondly, I think that XML is closer to doing it the right way than tech is. And the third thing is that I'm more likely to be able to get acceptance for this sort of technology in the XML world than in the tech world. And so I can sort of grow it over in XML, or try to grow it over in the XML world. And when it's nicely grown, we can move it over to the tech world.
Yeah.
I have a question for Nelson.
Yes.
When you were talking about storing it in memory, do you mean have the sort of master catalog of what's in TechLive in memory, or did you mean like pull in everything and have it, sitting in?
Potentially, I mean everything, because if, for example, you compressed almost everything in TechLive except the binary directories is a text file. Text files compress often by a factor of 10 to 30. So you could pull in the entire repository in a compressed form, and it would probably take less than 2 or 3 gigabytes of memory. And even modest laptops today come with 8 or 12 or 16 or more. My new workstation sitting right beside me here has a half a terabyte. So memory resident contents of large collections of files really is quite feasible. But you'd like to do it in such a way that the caching is oblivious to the user. The user doesn't know this is really happening. He or she just uses a handle on the object representing a string of text, and somehow that magically appears when a read or a get C call is made in a piece of software to get a character or a block of text.
Okay.
There's another way of looking at this, which is GitHub. I read some posts on their blog. There's something called cruft, which is sort of inaccessible stuff that you want to get rid of, but you're worried that it might cause problems if you don't get rid of it. And in order to reduce their storage capacity from so many petabytes to a smaller number of petabytes, they wanted to do a cruft removal process. And that requires a lot of processing of catalogs or indexes or whatever you want to call them, that sort of like car catalog sort of processing. And they put a number of developments into the way in which Git indexes and access stuff from pack files. So you have a pack file and you have an associated index file. And the upshot of it is that they are already developing, and it will get better over time, I think, very efficient software for handling massive quantities of data of particular type, of sort of programmer sort of type. So I think they have more data than the Library of Congress, or about as much, they said, that sort of size of data. And my attitude might be, well, there's all these sorts of opportunities available. I'm very pleased if the people who are experts at it solve it and solve all the caching stuff that Nelson is talking about. And I'm happy to have an opaque interface behind which things happen quickly, just as a solid state disk drive is an opaque interface behind which things happen quickly.
Right.
And so what we need for that to happen is a very simple interface that is, so to speak, uniform. And to say to the system, here's the object identifier, give me the stream that's associated with it, is precisely that sort of interface. And the system can then say, oh, well, this object identifier is very, very popular. Must be a GIF of a cat. I'll keep it in memory.
Right. Well, I mean, I was thinking about, for the typical author, how much of TechLive do they actually use? So that's why I was thinking.
Tiny amount.
A
a very
tiny
tiny
amount.
amount.
So that's
We
why
can, we can answer that question a different way. How long does it take to process a typical document? The first page of a typical document, a second or something. How much memory, how much material, even with a solid state disk, can a typical user get from the solid state disk in 1 second? You can't read gigabytes in 1 second.
Mhm.
If they process the document, first page of the document in 1 second, then I don't suppose they could have used more, I don't think it's sort of, so to speak, physically, logically possible for them to have read more than half a gigabyte in that time.
And also a reasonable figure to remember is a megabyte is one book. That's roughly 300 pages of 50 lines of 60 characters each. So the amount of text that's really needed for document processing isn't very big. And if you think of what Jonathan suggested of providing a transparent interface to this collection of text where you want to remove cruft, you could imagine, for example, that every string or every line in every file itself has a hash, and then you only store the unique line. So think of software projects that have a common multi-line copyright notice at the beginning of every file. You only need one copy of that. And so, for example, what I find when I compress log files from software builds where the same compiler command is invoked thousands and thousands of times, is that I can get anywhere from a 25 to a 100 times reduction in the size of a log file just by using high-level compression with XZ or LZIP. And that's really quite valuable. You have modern file systems now which implement compression at the disk level, but they tend to look only at disk blocks rather than at shorter strings. And yet a sophisticated compression engine, by looking at individual strings, can recognize lots and lots of commonalities and reduce them to relatively small amounts. And because they use variable length encodings, say a long string like Escherichia coli, which might occur frequently in a biology journal, could be reduced to 1 or 2 bytes. And so things like that help tremendously.
Can I ask, let me ask a question which David might not want to answer because of all sorts of reasons, but which is if, let's put it sort of hypothetically, there's a certain amount of money that an organization such as the archive spends on its servers that do tech typesetting. Now, if it's a few £1,000s a year, well, that's not that important. But if it's sort of £100,000 a year, then that is important. And there's this sort of question of what's, in broad terms, what would be the financial benefit to a particular organization of having a more efficient tech platform? Now, the sort of picture I have is that tech is not today, tech is not particularly computationally intensive. And I/O tends to be the slow thing. Now, a terabyte solid state disk for server use is a sort of fairly expensive beast. And if you've got a 12-core machine or a 16-core machine or whatever, I'm just thinking, what's the sort of financial benefit of having something that works closer to the theoretical maximum of speed? Because that would reduce carbon footprint and it would provide a route for obtaining funding.
In fact, a related question is that a repository like archive.org is in worldwide use, and there are service providers that sell commercial machines or time and cloud services that provide mirroring of such things. Does archive.org at present have mirrors spread around the world, or is everybody really pulling from the same physical
Well,
repository in a machine room somewhere on the planet?
we used to have a large set of mirrors, and they've kind of mostly gone away. There's still a few left, but we've sort of lost our focus on. We're not focusing on the mirrors anymore. We are migrating to the cloud, which will open a huge number of options in terms of mirroring around, different regions and things like that. So that's in progress, and that's going to take us a few years. But so we are. I mean, right now we have 10 VMs running at our Cornell IT service center, and those are just running for the sort of web. The web, we call them our web nodes. Basically, those are the ones you come in to browse, search, and all that. And our compilation is running on these. I mean, so basically, when someone submits an article, the compilation happens right there. And so one thing I'd like to do is basically create this cloud-based compilation service. We have parts of it are done. So instead of having to copy tech live onto every server that we run, basically have this service that's responsible for doing that. And we actually have more servers than that. So we have a bunch of export servers than the mirrors. So dealing with tech is a lot of work. And so I'm thinking about this whole idea of being able to pull these files from somewhere else. I think the last time I downloaded Tech Live, I think it was maybe almost 9 gigabytes. I mean, it was massive. and I think I kind of like the idea of like, maybe just download this catalog, which may be much, much smaller. And then as you run things, you just build up your own cache. And I suspect if we did that, we'd still have a tiny portion. We'd be using a tiny portion of what comes in Tech Live. And then I think about all of the people out there that download Tech Live. I'm like, wow, this would be like a major win for them, in terms of just pulling in what you need. So I'm just kind of thinking about,
Well, you're very welcome to think and come back and share. We can make you a special guest. We're very pleased with that. There's a thought I had that I'm going to share with you, which is that if I'm a solitary author of mathematical papers, which I occasionally am, there are 3 tech installations that are important. The one on my machine, the one on the archive, and the one in Overleaf. If I'm a collaborator, then my collaborator's platform is important. And if I'm submitting it to a journal, then the journal's platform installation is sort of important. So that's sort of about 5 of them. Well, this is a situation where knowing that the installations are giving identical results and having identical inputs can be enormously helpful. And if the installations are effectively reproducible, I think this is the thing, is the reproducibility of the installation. And as far as with Ruby, you have what's called the gem file, and these are the resources that the thing uses. And you can run Ruby in such a way that you only pick up things that are in the gem file. So that's a catalog. And Elm, a web framework for a framework for web page, JavaScript and web pages, also has a similar sort of process. So the tech installations can be different, but if a document uses a catalog, if the document entirely comes from a catalog, All that matters is, does the installation support the catalog or not? If the document has a catalog and the catalog is supported by the installation, then you should get the same results. And if you don't, it's a software problem and not a installation problem. So that's really what, in some sense, what the catalog is doing. The catalog was originally designed to allow for portability of XML documents that depended on external resources. But if we put into them the Git object identifiers, then we also get a much stronger form of reproducibility, because we don't have to check that they've got exactly the same version of the schema or whatever it is that we're using, or the font. We know they have because it's been accessed through the object identifier. Nelson, you mentioned something to me by email tonight today, and I wonder if you'd like to share some of it before we close.
In previous discussions on this list, several times the issue of creating documents for relative novices has come up, and a number of people have expressed the idea that Markdown is a very simple markup language that is relatively easy for people to learn and produce documents. Well, about 2 weeks ago, I saw a Google News item about an editor I had not heard of before called Ghostwriter, Ghostwriter, that is in some of the Linux distro package systems, including recent Ubuntu, but not in CentOS or Red Hat. It's also available on GitHub. And what it does is provide a GUI editor where you can create input on part of your screen. And as you edit the document, you see the essentially formatted output in real time on another part of your screen. And we have almost no experience with this yet. The two of us have tried it, and it seems to come up and work. And at least for people who aren't particularly interested in learning about XML or TeX or LaTeX or any of these other systems, Markdown is probably a pretty good solution. Kelly Johnson, who's been a frequent attendee at these sessions, works with a number of authors working in the fisheries part of the federal government. And these are people who aren't technical people. They're document authors. Their job is preparing documentation to describe government research projects. And they don't want to learn anything more than necessary to do their job. And so an editor like Ghostwriter in fact could be quite helpful for them. Now, of course, an issue with text editors is if you use more than one, your fingers and your brain get confused, and you type the wrong commands into the wrong one and mess things up. So some of us have rather strong religious views about text editors. I'm in the Emacs camp because I've been using it for more than 4 decades, and it does pretty much everything I want to do. But we have to realize there are lots and lots of people who really want to learn the minimal amount about computers in order to do their job, such as a writing job. So I think it's worth spreading the word about Ghostwriter and getting other people's feedback about it.
I think it's really important that people that use Markdown should have access to high quality typesetting, by which I mean decent fonts, decent line breaking, decent hyphenation, mathematical typography if they need it.
Yeah. Now, the other thing that happened this week was yesterday, the team that produces TechInfo announced a preliminary test release of what will be a major new release, TechInfo version 7. TechInfo is a system that came out of work done in the roughly mid-1970s, where the goal was this. Remember, this is before TeX, before SGML and XML and HTML and the web and PostScript and all of these other technologies. They wanted to have a way to, with relatively simple input, to produce documents that were displayable on a computer terminal with a fixed width font, and that were extensively hyperlinked so that you can follow links forwards and backwards. One of the problems of web browsers, they make it easy to follow a link forward, but they don't make it so easy to get back to where you were before. And yet often that's how people navigate large document collections. They jump temporarily to a dictionary that explains a concept they didn't understand, and they want to get back and continue reading the main document. So TechInfo then was a system that was built on top of the info format, which was very, very simple. And the new features announced this week are support for LaTeX output as well as EPUB output. It's produced PDF files and info files for decades. So I'm sure we will be playing with this as well. My experience up to now with TechInfo is it's fine for that kind of documentation, documenting computer programs. It isn't fine when you want to discuss mathematics, physics, chemistry, and more complicated things, where you need color or you need control of page layout. It doesn't have the concept, at least yet, of document styles and classes where the same markup of chapter, section, subsection, and so on could produce extremely different document appearances depending on what grammar file you loaded for defining what those particular markup commands mean. This certainly could change in the future. There's no reason it shouldn't, but at present, in my view, it's a pretty limiting format for technical documentation, and certainly would not do for archive.org with their diverse needs for multiple scientific subject areas now being covered.
I think there's an enormous amount of work to be done, and it's not really for sort of hardcore technical people. It's more for human computer interaction sort of people and that sort of thing, is managing information from disparate sources. We're sort of quite good at managing information from a single source, a single website. But when we've got multiple sources going on. And I was very impressed by the simplicity and ease of use of TechInfo. And I think there's a lot to be learned from the problems tackled by the early systems and the ways in which they solved them. Let's put it that way. That so the man pages are sort of a classic solution to a sort of important problem, and we have to understand these sorts of devices. It's like a musician, not that I know much about music, has to understand all sorts of musical capabilities of instruments and of tone and of rhythm and all that sort of stuff. So the various sorts of ways in which documents can work, both in authoring and reading and indexing and searching, is actually, I think, a really important area. It's sort of information management, if you like, and it's to a certain extent it's library science, isn't it? Sort of how do libraries work? I'll stop. Anybody wants to add some more remarks? They're very welcome to.
I'll just toss in a comment.
Yeah.
Oh, go ahead, David.
I was just going to say that Christopher posted a comment in chat about Markdown and semantic annotations, and that could kind of impact the accessibility side of things, I think. So.
Yeah. I just wanted to comment that, interestingly, TechInfo and LaTeX have a little bit of history in common, because although Donald Knuth decided to use a backslash to start commands in Tech, Brian Reed at Carnegie Mellon in roughly 1976 to 1980 used @ so @ chapter and so on. And the @ we have today in BibTeX, because the scribe bibliography format is the same pretty much. as the LaTeX and BibTeX format is. And when Leslie Lamport wrote LaTeX, he used the backslash from tech, but he used the idea of logical markup that Brian Reed's scribe had introduced. Namely, you don't want to have the author worrying about the output appearance. The author should concentrate in saying what the logical items, the chapters, sections, tables, and so on are in the input stream, and leave the formatting up to some other piece of software to get a particular output appearance. And that's a lesson, sadly, that has not been learned in the word processor community, although modern word processors do have style sheets. At least the people I talk to don't seem to know anything about them and don't use them. They simply edit away, pulling down menus, picking fonts, and moving text around to make it look like they think it should look on the printed page, and have completely lost, or perhaps never had, the idea that there's a logical structure in the document, and it makes sense to exploit that. Because if you don't exploit it, then what you'll end up with is chapter 1 will use a particular font and a particular size, and chapter 17 will have a different font and a different size, and you'll get an inconsistent document. So my view has always been that word processors are fine for 1- and 2-page documents, but they really aren't suitable for writing longer things, because you're going to have to work very hard to ensure consistency, and consistency in big documents is one of the biggest problems you have as an author. In fact, when we visited Don Knuth at his house 3 or 4 years ago, he told us that he has done something to handle this problem of making sure he doesn't repeat himself. He has all of his writings from his entire career collected on the same computer and all carefully indexed by sophisticated software, so that if he's about to cite a particular paper, he looks up in that index to see how he cited it before, and decides whether to add anything to it. And he can pull up a quotation that he's collected, because he might find that useful as an epigraph in the chapter. And I think that was a really nice way of managing his writing career, which has been enormously productive, and also, compared to any other author, enormously correct.
I think we could perhaps have a session on, I don't know what to call it, the writer's workbench. Perhaps there's a better name. What would you call it, Nelson?
Yeah, well, the writer's workbench was actually a flavor of Unix developed at Bell Labs during the 1970s and early 1980s. But it seems that Bell never made it a commercial product, except possibly to a tiny number of customers. And so you can certainly find papers in the literature that refer to the writer's workbench. And a few of the tools that were produced for it are still available. Mostly it never became part of the mainstream Unix distributions from other companies and other universities. So it's kind of a historical note at this point. And as we're discovering on the Unix Heritage Society list, it can be quite difficult to reconstruct what happened when Unix was being developed, not only at Bell Labs, but at numerous universities around the world. And people were mailing stuff back and forth and contributing changes, and didn't have at the time Git or RCS or CVS or any of the other revision control systems. So it has a very muddled history. But nevertheless,
I think it's really valuable to have prior art available to know about it.
And the writer's workbench was motivated by the desire of Bell Labs to have tools to make document preparation for a very large corporation relatively straightforward. It's one of the biggest companies in the United States.
Instead of telling us about it now, how would you like to be a special guest and tell us about it at some future time?
Yeah, I'm sure that could happen.
We could find other people to help you with it.
Yeah, maybe in the winter or spring. I'd have to do some background research to pull up some things. But
you could what's the word? Present a rough talk and use it as a sort of part of your research.
Well, just as a couple of examples of things I've done myself, because there wasn't any tool available in the Unix world. One is finding doubled words in documents. In the house is a common mistake, because you put a carriage return after the first the and start the next line with another the. And the second one is checking delimiter balances, which are incredibly important for getting tech input to parse correctly. You leave off a brace or insert a brace that doesn't have a matching one, and you're in deep trouble. And it can be very, very hard to find these things in large technical documents, especially when authors, as many of our students do, write one paragraph per line. So their lines are thousands of characters long. So I wrote check delim and DW to solve this problem, and they've been available for decades on our website, but they've never been part of the standard Unix toolbox. Now, some word processors will flag doubled words. Emacs will do that as well if you turn on a special option. But that's only part of the problem. The delimiter balance is much, much harder and deserves special software.
Oh, Christopher, we're getting on to
He's pretty
Cecil
busy.
Carlton, I think they're called. Yeah. Zettler and little notes, and I think it's Obsidian is one of those things. Yeah, the sort of the small tool, the tools for sort of index cards and that sort of thing, but linked. It's the links that are as important as the notes.
Obsidian, in particular, it's a Markdown-based editor, but it lets you set it up as a hierarchical, linked system. I think it's pretty fun. I like it.
Yeah, Hypercard is one of those. It's rather different flavor, but it's a sort of small information management tool.
And
Yeah.
that one allows scripting, which I really liked.
Yeah.
That was a cool thing about HyperCard, is you could script it. You could write little applications on cards. You could have useful cards and you could have information cards. But unfortunately, Apple didn't want to keep that one up.
I've never owned a Mac, but I had an opportunity to buy a second-hand copy of the HyperCard book, and so I think I still got that. So I can, if we hold a meeting on that, I can bring that in.
VoodooPad was, for a time, sort of like HyperCard, where it was both a wiki and also you could embed scripts into it. That it was bought and sold a few times, and now I think they've taken out the scripting part, so it's a different product than it used to be. But it was a really interesting idea that I think never got the development it needed.
Another pad project that I think product, which I think is very, very interesting, is Etherpad, which sort of provides this collaborative editing, online, instant real-time collaborative editing, similar to Google Docs. So I think that the enormous difference today with the Writer's Workbench is the fact that we're electronically connected with each other, and possibly also video connected with each other. Although that said, perhaps it's time to bring this meeting to a close.